and welcome to the webinar. So my name is Mark McDonald. I've been working at the National Engineering Laboratory for the last 8 years now, and since 2018 I've been leading the Clean Fuels Metrology Group. So this webinar is very relevant to all of the projects I work on, and I hope you find it as interesting as I do. So there's a couple of different sections to look at. First of all, we're going to look at the National Measurement System, which is a structure in the UK, and overall the importance of measurement and why it matters to us. Next, we're going to look at some of the considerations for measurement in terms of achieving net zero emissions and reaching these targets for carbon dioxide emissions reductions. And finally, we're going to look at some of the plans, test facilities and infrastructure from NEL or the National Engineering Laboratory in terms of the Clean Fuels Metrology Centre. So to start off in a very simple form, what is the overall role of measurement in industry? Now, as we see it, it provides structure and provides efficiency. And basically, if you have accurate measurement, then that enables trade to occur, because for trade to occur, people need to think that the transactions that take place are accurate, fair, and legal. And that accuracy ultimately comes from traceable measurements. So it has an important enabling role in the UK economy and in the wider world as well, both for the individual and for companies and larger organizations. The interesting thing about measurement is if it's done properly, it tends to be invisible, at least to people who don't work in metrology. So an example of this would be the last time you refilled your car, did you think about how accurate the measurements are? And most of us don't. Most of us just assume that they are perfectly accurate and you get exactly the right amount. That isn't strictly true, but the measurements are accurate enough that they serve the purpose required. And that's really how things should be. So the average person should not really be thinking about accuracy of measurements because it shouldn't be an issue to them. And we can say that as a metrology institute, we are doing our job properly if the measurement is not greatly noticeable to people. So quite often it's the case that measurement only becomes visible when something has gone wrong and the errors are unacceptably high. With that in mind, the UK has an interest in promoting good measurement practices and ensuring that measurements that take place in the economy are accurate, fair, and legal. So we have an organisation, we have a structure in place which is called the National Measurement System, which is put in place by government departments. The government department, the business for Business, Energy and Industrial Strategy, or BEIS, which invests £65 million per year into this structure. And what it does is basically maintain the UK's measurement traceability chain and develop documentary standards and promote knowledge transfer of the best measurement practices. And it has a very important role when we have cases of large sector-wide challenges that are not traditionally met by private organisations. So it's especially important in times like this when we are thinking of the transition to clean fuels, which cannot be addressed by private organisations alone. So within the UK National Measurement System, TÜV's National Engineering Laboratory, or NEL as most of you know us, we have the role of a designated institute. So we have responsibility for the national measurement standards for flow and density measurement. And there's other organisations that are part of this structure. So you have the National Physical Laboratory, or NPL. You have the National Institute for Biological Standards and Control. You have the National Measurement Laboratory of the LGC. And some other organisations as well, such as the Office for Product Safety and Standards. So they have more of a regulatory role. The other organisations, they develop primary reference standards for measurements, whereas the OPSS is more about enforcing regulations and making sure they're actually followed. And there's also the gear metrology unit at Newcastle University. So they're concerned with metrology as it applies to gears and measurements of that type. So the overall structure looks something like this. We have a traceability chain with BEIS, or the Department for Business, Energy and Industrial Strategy, right at the top of the pyramid, together with the Office for Product Safety and Standards. And they're really responsible for setting the regulatory framework and making sure it's actually followed, and basically promoting good measurement practices within the UK economy. The next level down is the NMS laboratories, such as NEL, and this is where the physical and documentary standards for various different measurement types are developed, and these serve as a reference point for the measurements taken in the wider economy. So the next level down from that would be accredited laboratories, which are not part of the national measurement system, but are traceable to those laboratories. And we continue to move away from the top of the pyramid. And as we're doing this, we're increasing the overall level of measurement uncertainty and decreasing the overall level of accuracy. But we still maintain this traceability as we do this. So within most companies, there is a department for quality control and quality assurance. And part of what they do is make sure that the relevant measurements are backed up by calibrations which are ultimately traceable to standards and possibly the national standards for that country. Finally, when you get to the bottom stage, this is the wider marketplace for end users, and we might expect that measuring devices at this level might have a slightly higher measurement uncertainty, but again, that traceability has been maintained at each step in the process, so we have something solid to point to say this is how we know our measurements are accurate enough for the application. So that gives you an overall sense of where we sit in the overall measurement structure. So we can now start to look at the challenge of net zero and what are the drivers and what are the challenges for this. So there's many different drivers actually, and you can see this because there's various countries in the world that are starting to think the same way on this issue. So we have things like the Paris Agreement, which is internationally recognized, and this has the aim of reducing or limiting the global temperature rise associated with greenhouse gas emissions. So the aim is to limit the temperature rise to less than 2 degrees, or ideally less than 1.5 degrees globally. You also have a Renewable Energy Directive. This is a directive set by the European Union, which promotes the use of renewable energy. There is the European Green Deal, which has an overall aim of making Europe climate neutral by 2050. And within the UK, we have the Climate Change Act, which has a similar goal, which is to make the UK carbon neutral by the year 2050. So these are quite ambitious targets, and there's various different strategies for how this can be achieved. But at least within the UK, we can see that the heat and transport sector are really crucial to this. So these are both sectors which are responsible for a huge amount of the carbon dioxide emissions currently generated, about 56% of the total. So strategically, these have been pointed out as some of the priorities for decarbonisation. So if you can decarbonise heat and transport, then that gets you a long way towards removing those carbon dioxide emissions and meeting the required targets. So the UK government issued a document known as the Clean Growth Strategy in 2018, and this identifies various different mechanisms and technologies for which these targets could be achieved. And it includes things like the role of electrification, so generating electricity from solar and wind sources, for example, using battery electric vehicles and using heat pumps for heating of homes. It also recognised the role of biomass and bioenergy. So we've seen lots of anaerobic digestion plants have been built in the UK in the last 5 or 10 years. The role of hydrogen appears in many different places because it has tremendous potential as an energy vector. And finally, the role of carbon capture, utilization and storage is still recognised because we expect to still generate some carbon dioxide emissions depending on what energy sources we use. It might be from biogas, it might be from fossil fuels in the interim, or it might be from hydrogen, which is ultimately generated from fossil fuels in some cases. So there will still be a need for capturing carbon dioxide to meet those targets. If you look specifically at the role of hydrogen, I mentioned that this appears in various different places, and I'm not going to go through every one of these individually, but it has a role in mobility through the use of hydrogen vehicles. It has a role in heat, because if we can replace natural gas with hydrogen in the UK gas networks, then we can reuse the existing infrastructure, which has seen billions of pounds worth of investment over the years, and we can reuse most of the same staff who have the same experience, which has been developed over decades. So this would be quite an efficient way to decarbonise heat if we can replace natural gas with hydrogen. Hydrogen also has tremendous potential for energy storage. So one potential use for this is to generate hydrogen from electrolysis with the energy supplied from solar or wind energy. So those are intermittent sources, and the hydrogen could be used to even out the peaks and troughs, which would mean you could get greater overall energy utilisation. And it means you would have a means for energy storage in the short and long term. And there are some implications for industry as well. Not every process can be heated using electricity. Sometimes you need direct flame applications, but it doesn't mean you have to use natural gas. You could potentially replace that with hydrogen, which is cleaner burning. And for energy transport as well, the hydrogen can be transported through various means. It can be transported as a compressed gas through pipeline, or it can be transported through gas cylinders. It can be liquefied. It can be stored in metal hydrides. There's many different means for how you could transport energy in the form of hydrogen. At this point, I should mention an important activity we've been involved in, which is as a member of the European Metrology Network for Energy Gases. Now, this is a network that consists of 17 different metrology institutes from all across Europe, and it really aims to facilitate the move towards renewable, clean fuels with a focus on energy gases metrology. So there's various different activities planned by this network. First of all is to develop a strategic research agenda, which identifies the key measurement gaps and challenges in order to meet this transition to renewable clean fuels. There's also going to be a measurement service platform developed. So this will be an online service which you can use to determine who has measurement capability for your application with energy gases. And this would include national measurement institutes, but also other accredited labs that want to be part of the measurement service platform. And overall, the network has an important aim to improve dissemination of research results from European metrology activities. So this is including dissemination into industry, but also to policymakers and standards organizations to really get the best conversion of those important findings from critical research that's been taking place. If we just look at the first objective, which is publishing the strategic research agenda, well, we've made some progress on this recently. There was a workshop hosted at the National Physical Laboratory in Teddington back in January of this year, back when people were allowed to attend workshops and conferences. And this was attended by various different organizations from gas providers, equipment manufacturers, calibration laboratories, and members of the European Commission, standardization organizations, and many more. The overall purpose of this workshop was to discuss and prioritize the energy gases measurement challenges, which would enable us to make the transition to renewable and clean fuels. So from the workshop, we came out with the following priority measurement challenges, which include flow metering of hydrogen vehicle refueling stations, energy metering for hydrogen and other non-conventional gases, so things like biogas and biomethane, for example, if they are injected into the gas grids. And the energy metering consists of flow measurement, but also determination of calorific value and gas purity and quality. There's also a need for validation of online gas analyzers for quality assessment, as well as better practices for generating representative samples. So you can see there's many different areas that these cover. To be honest, I mentioned before that we are the designated institute for flow metrology in the UK, so we are really biased towards the flow applications. But if you want to find out more about these other applications and the network itself, then I encourage you to follow the link on the Euromet website. But now I'm going to talk a bit more specifically about what we're working on. So the areas that we are prioritizing at the National Engineering Laboratory, or NEL, are flow metering for hydrogen vehicles and hydrogen refueling stations, flow metering for gas within the UK gas networks, flow metering of carbon dioxide and CCS mixtures, and flow metering of liquefied natural gas. If we start with the first one, which is hydrogen vehicle refueling. So what is the attraction to using hydrogen vehicles in the first place? They're actually very similar to electric vehicles. The main difference is how they are fueled. So the refueling process, instead of charging a battery, you refill a compressed hydrogen tank. And the advantage to doing this is that it takes only around 5 minutes to do so. So rather than spending hours charging a battery, you can do this fairly quickly. The overall process is quite similar to using a petrol car and filling it up at an existing refueling station. The main advantage is that you get greater range with these vehicles, but otherwise they're actually very similar. So hydrogen vehicles are also quiet and very efficient. They don't generate carbon dioxide emissions, and they share a lot of the same components as battery electric vehicles. So the main difference is just how they're refilled and charged. But to enable the use of hydrogen vehicles, I mean, the cars already exist, and there are some refueling stations as well, but there is not a sufficiently robust network of refueling stations to enable the average person to drive one of these cars. So a lot of work has to be done. And one of the main concerns is accuracy. So I mentioned before, if you refill a petrol car right now, you don't really think about the accuracy of the dispensers, but that's not the case for the hydrogen dispensers, because some more research has to be done in this area. So there are targets for accuracy which are set by the international standard or the international recommendation OIMO R139, and it recommends class 2 or class 4 accuracy. The requirements for class 2 accuracy are that the overall measurements from the refueling station must be accurate to within a maximum permissible error of less than 2%, which corresponds to 1.5% for the flow meter itself. And this is actually really challenging because the measurement conditions at a hydrogen refueling station are not easy from a flow measurement perspective, as we can see. So because we need to achieve a good energy density, the hydrogen has to be compressed. In the vehicle, it will be compressed to around 700 bar for a light-duty passenger car. So within the refueling station itself, you can have pressures of up to 900 bar. The refueling process is also very quick, which means you generate a lot of heat when you compress the gas into a tank. So to prevent the temperature rise from being excessive, the hydrogen is first pre-cooled down to -40 degrees C. So these ranges of pressures and temperatures are not easy for most flow meter technologies. At the bottom of this slide, you can see a diagram, a simplified schematic of a hydrogen refueling station. So what it consists of is a source of hydrogen gas, so either generated from electrolysis or supplied from gas bottles. We then have a compressor to raise the pressure up to 900 bar or so. And we also have a pre-cooler to reduce the temperature to -40 degrees C. And finally, the hydrogen is delivered at high pressure and low temperature to the receiving vehicle. Now, there's various sources of measurement uncertainty here. So first of all, well, the temperature and pressure ranges could be challenging for the flow meter, but we also have things like the dispenser hose, which must be vented after use for safety reasons. So that represents a quantity of fuel that's been measured by the flow meter but not delivered to the customer. So that has to be accounted for, otherwise it forms part of the measurement error. There are also dead volumes in the refueling station. So these are sections of pipe which connect the outlet of the flow meter to the receiving vehicle. And those sections of pipe will be filled and emptied during the refueling process. And depending on the sequence, the mass in those sections of pipe can change, and that's what's called a dead volume. Again, that has to be accounted for, otherwise it forms a large part of the measurement error. The location of the flow meter also matters, so there's two locations shown on the diagram. There's upstream and downstream of the heat exchanger, and depending on where it's installed, the pressure and temperature conditions can be very different. So you can imagine that the flow meter installed upstream of the heat exchanger will typically be around ambient temperature, whereas the one installed downstream can see temperature ranges of ambient down to -40 degrees C. So that has important implications for the measurement accuracy. So we need a means of determining and demonstrating the accuracy of these hydrogen dispensers. And there have been some developments in this area quite recently. So a number of field test standards have been developed by various organizations. So in the USA, there's been NIST and NREL. There's also, in mostly Europe, the gas provider Air Liquide has developed a system. And within the European Joint Research Project, metrology for hydrogen vehicles, 4 have been developed by different NMIs. So Metas, VSL, JIV, and Force Technology have all developed one of these systems. And they all share quite a few design similarities. They all have a collection vessel and a weighing scale. And the idea is that the system takes the place of a hydrogen vehicle. You dispense gas into the tank, and then you weigh it afterwards. And you compare this with the flow measurements from the hydrogen refueling station. So in principle, it's quite simple. The implementation is a bit more complicated, but you get the idea. If you want more information on these systems and the measurement uncertainty and the design, there is a paper that's been published by Metas, and that's in the Journal of Measurement and Implementation. The reference is below that photo, but you should be able to find it online quite easily. It's open access as well. So there will be a link to this on the Metro Hive project website, so I'll mention this again in a following slide. But we have some results from actual tests at refueling stations under real conditions. So these results were provided by Air Liquide using their field test standards. And what we're looking at here is test results from 2 different refueling stations. And in both of these, the flow meter was installed upstream of the heat exchanger. So it's the same general configuration. And what you can see is that the errors are different for each refueling station, but we can see a similar trend at both. Now, what those circles correspond to, the different series on the graph, these are different filling procedures. And they start with the blue series, and then they work their way down to red, yellow, and green in the same sequence that you can see on the legend on those graphs. So the blue series, this is a full fill. So this is an empty tank that's been filled to 700 bar. The red series is a partial fill. So it started empty and you filled it to 350 bar. And then the yellow series is from 350 to 700 bar. So you get the idea. And what you're seeing with this trend of positive and negative errors is actually the effect of the dead volume in the hydrogen refueling station. So this hasn't been accounted for, and this is why you're seeing this distinctive trend at two different refueling stations. I'm not going to talk about this in too much detail, so again, if you want to read about this in more detail, there is an open access journal paper available. The reference is below this slide. It's in the Journal of Flow Measurement Instrumentation, and you should be able to find it from the MetroHive project website as well. But the point is, there's been some research in this area, and much more has to be done. So this is something that NEL is going to work on as well, and we're going to develop our own field test standard to do the same type of research. But the general findings are fairly interesting. We can see that potentially the meters the flow meters installed at the refueling station can meet the requirements of the OIML R139 standard. But there is a caveat to this, and that is the fact that there's many sources of measurement uncertainty, which can actually increase the error quite dramatically. So there's things that have to be taken account for, such as dead volumes and the effect of temperature, for example. But it demonstrates that there is a need to go to the refueling stations and test under real conditions using these types of systems. At the same time, there's still a need to test the flow meters in isolation, not so much the refueling station as a measurement system. So you might have to do this if you're going to calibrate the flow meter before it's installed, or for type approval testing. And there isn't really any easy way to do this right now, because there are no independent traceable flow facilities that can operate with hydrogen at 700 bar and minus 40 degrees C. These facilities just don't exist right now. So we need to look at alternatives. And that's something that was considered in the MetroHive project. So we looked at alternative calibration methods using nitrogen and air. So the basis for this is that we recognise that the flow meters used at hydrogen refueling stations are all Coriolis types at the moment. And the Coriolis flow meters are generally quite insensitive to fluid properties, and they provide a measurement on a mass basis. So we decided to test with nitrogen and air at a representative range of mass flow rates, and we also decided to match the density as close as we could to hydrogen at the real conditions. So we can do this because hydrogen is a very light gas. At 700 bar, the density is only about 46 kilograms per cubic meter. So that's equivalent to nitrogen or air at about 40 bar. And that's the basis we use to investigate this test and calibration method. So the series of tests looks something like this. We had testing the ambient temperature and two different pressures, 20 bar and 40 bar using nitrogen and air. We also did tests where the effective temperature was isolated. So we studied the effective temperature under stable conditions from temperatures of minus 40 up to 40 degrees C. So an overall range of 100 degrees. Next, we also investigated the effective temperature under transient conditions. So this was done by introducing gas to the flow meter at very low temperature. So the meter was initially at ambient temperature, and there was no time allowed for the flow meter temperature to stabilize. So measurements were taken as the temperature was adjusting to the incoming gas. The effective pressure was also studied in isolation by the Swedish Metrology Institute RISE using water at up to 850 bar. And finally, a flow meter that had been tested at using each of these test procedures was also installed at a hydrogen refueling station and tested under real conditions with hydrogen. So you can see some of the gas laboratories which were used for the experiments. We can see the National Engineering Laboratory, or the NEL test setup on the left. We have SUZAM on the right, and we have METAS as well. And each of these installations were quite similar. We all operated in gas blowdown as an open loop. The reason for this is that the pressure drop across the flow meters was very large, in some cases up to 10 bar. So we couldn't operate in a closed loop configuration, and we all used either nitrogen or air for these tests. And generally the results were very interesting. We saw some good results for the ambient temperature tests. So the errors were generally in the range of 0.5 to 1% for the ambient tests. We saw a small influence of temperature under stable conditions. So this is what the graph on the right-hand side at the top shows you. So we have 3 different series. The green is 20 degrees C, the orange is 40 degrees C, and the blue is 0 degrees C. So we can see that at medium to high flow rates, there isn't really much of an effect of temperature, but at the very lowest flow rates, we can see large errors at the high and low temperature condition. The effect of pressure is shown on the graph at the bottom. So this shows a pressure range from 100 to 850 bar. And you can see the effective pressure isn't really perceivable, it's very small. So we didn't really see a pressure effect in testing with gases up to 86 bar, and in the liquid tests with water up to 850 bar, the effect was estimated at 0.0001% per bar. So that's quite insignificant compared to the kind of uncertainties that we have to achieve at hydrogen refueling stations. Something that wasn't insignificant though was the effect of temperature under changing conditions. So again, this is when the flow meter is initially at ambient temperature, and then you introduce a cold gas and you don't give it time to stabilize. And we can see the results on the right-hand side here. So it's quite a complicated graph, but I'll just explain it very quickly. The graph at the bottom with the red, green, and blue series, these are different temperatures at various locations, and the x-axis is time over the course of 5 minutes or so. The graph on the top, this is the flow measurement error for 2 different repeats of the same test condition. So what we can see is that over the course of 5 minutes or so, as the temperatures began to stabilize, we saw errors ranging from -15 up to +5%. So those are very large. And this has important implications for the hydrogen refueling stations, because if the meter is installed downstream of the heat exchanger, it could be exposed to this effect. So this is one more thing that has to be accounted for, and it really shows the importance of assessing the hydrogen refueling station as a complete measurement system. But overall, this approach was successful. We found that using inert gases like nitrogen and air can provide a useful means for calibration and type approval testing. If you want more information on these tests, they will be published soon in journal papers. So they haven't been finalised yet, but they will appear in the Journal of Flow Measurement and Instrumentation. Again, they will be open access. To see all of the papers, I would encourage you to go to the Metro Hive website, and there's also going to be reports and presentations and various other resources published there. But that about covers it for hydrogen refueling stations and hydrogen vehicles at the moment. Another area we're interested in is hydrogen for heat, or replacing natural gas in the grid with hydrogen, either as a pure gas or as a blend. So there's various projects looking at this right now, but the focus has been mostly on safety and customer acceptance and a lot of the technical practicalities. The focus hasn't really been on flow measurement until quite recently, and that's understandable. But it is actually quite a big concern as we move more towards a practical solution and gaining public acceptance. Because as I mentioned earlier, the average person wants to know that the measurement is not an issue and it's more than accurate for the application. So there's various projects looking at this within the UK. We have quite a good awareness of H21, which is operated by Northern Gas Networks, H100, which is operated by SGN, High Deploy, which is run by Cadent, and High for Heat, which is run by Arup. So in each of these projects, the role of flow measurement is starting to become more and more important. And the reason for this is that hydrogen has quite different fluid properties compared to natural gas, and that has an implication for the flow measurement. So one of the biggest differences is a decrease in calorific value. It's about 3 times less for hydrogen than it is for natural gas. This means that to achieve the same energy density, you'll likely have to increase the flow rates. So a flow meter currently working at 6 meters cubed per hour would probably have to operate at around 20 meters cubed per hour if it was using pure hydrogen. And you can imagine that existing flow meters would become overranged. And with mechanical type flow meters, that could contribute to increased wear or premature failure of the meters. But at the very least, we'd expect to see increased measurement errors. There's other fluid properties that are important as well, such as gas density. This is 8 times lower for hydrogen compared to natural gas, and the speed of sound is 3 times higher. The viscosity is in a similar range. That's not quite so much of an issue. You can see on the right-hand side, this is a screenshot from the standard for ultrasonic domestic gas meters, and these are recommended test gases that are currently used. And you can see there's nothing in there that really represents hydrogen or something close to a pure hydrogen. So there's obviously work that needs to be done on the standards as well as in developing the evidence for the performance of each technology. In terms of the technologies available, there's 3 different types of domestic gas meters that are widely used in Europe. Within the UK, it's mostly diaphragm gas meters, about 80% of the installations, and the remaining 20% are ultrasonic meters. We don't tend to use thermal mass meters for domestic gas metering in the UK, although they are used in Europe. And we can see we are anticipating different reasons for increased errors for each of these devices based on their response to the hydrogen fluid properties. So for diaphragm meters, we're concerned about the meters becoming overranged, but also increased slippage or internal leakage due to the fact that hydrogen has a smaller molecule size and a smaller density than the other gases. With ultrasonic meters, we're concerned about the change in acoustic properties. So the existing transducers are probably not suitable for this change in gas. And with thermal mass meters, assuming that the heating element and the sensing elements are appropriately spec'd for the fluid property ranges, then they could perform quite well with the pure fluids. But you could imagine with a variable mixture, if hydrogen is injected into the gas grid, then you would have to continuously update the fluid properties or work within a limited range. So this is all not speculation, but we anticipate reasons for increased errors for each of these meters. But what we really need right now is evidence. So we need to have a test program to actually get that evidence. And this is a problem because there's no existing facilities that can do these tests. And if you are to build one, where do you start? I mean, what do you use as your reference device for hydrogen if there isn't any obvious choices? So this is something we're working on right now, and we are building a facility for domestic gas meters that can be operated with hydrogen or hydrogen and methane mixtures. We're at the build stage right now, so we expect this to be finished around August or September this year. So this is a simplified P&ID diagram of the facility we intend to build. It looks quite complicated, but that's just because we have 2 different inlet streams for the mixtures. The general principle is quite simple. We have a pressurized gas supply, and we blow down to atmosphere. We have individual reference meters, then we have the combined streams which are mixed before the test section where the meter is installed, the test meter. In terms of the operating ranges, we have a maximum flow rate of 50 standard cubic meters per hour. We can operate with pure fluids or mixtures of hydrogen, methane, and nitrogen. The expected measurement uncertainties are 0.2% for methane and nitrogen for the mass flow rate and 0.3% for hydrogen. The test conditions at the test section, this will be low pressure because domestic gas meters are typically used at 20 millibar. So it's not really a high pressure facility, although the temperature range should be quite wide. So we're expecting between temperatures of -25 and +55 degrees. It's a relatively small scale facility, but we expect to be able to test many different types of meter, not just domestic gas meters. In terms of the reference devices that are used, for the flow reference devices, we're mostly using sonic nozzles, but for the very smallest flow rates, we're also using laminar flow elements. But that gives you an overview of the first hydrogen facility that we're intending to build. Now, the next area that we're working on is flow metering for liquefied natural gas. And obviously, liquefied natural gas is still a fossil fuel, but the reason you would want to use that in place of liquid fuels such as diesel, for example, is that it burns much cleaner. So the sulfur content, the NOx emissions, even the CO2 emissions, these are less for liquefied natural gas than they are for diesel. So at the moment, LNG is traded in the form of energy, which means you have to measure the volume, the density, and the calorific value to get an overall energy value for the fluid. The standards that are followed come from the GIGNO and the ISO 10976 procedures. At the moment, the volume measurement is typically done by tank gauging methods, and there's quite a high financial exposure associated with measurement uncertainty. So within the EU alone, a measurement error of 1% corresponds to nearly €1 billion per year. Then more recently, there has been a move towards using flow meters for the measurements instead of the tank gauging methods. And the advantages to doing this is possibly greater accuracy and lower capital costs. However, there needs to be reference methods to prove that the flow meters are accurate. So we need test facilities and calibration methods. And this is really challenging because LNG tends to be used at very high flow rates and large pipe sizes. So the type of test facilities you need to verify the flow measurements are very expensive. They're not only large, but they're also operating at cryogenic conditions. So there has been quite a bit of research in this area, especially within the EU-funded LNG MPA projects. So we're actually on the third of those projects right now. And the aim for these projects is to develop test facilities and verification methods, first focusing on the small scale applications like trucks and heavy goods vehicles and buses, but eventually with a scale up to the larger applications like loading and unloading for shipping vessels. So the first two projects have been completed already, and we're getting towards the end of the LNG3. And within these projects, an LNG facility, the first of its kind, was developed, and that was developed by VSL in the Netherlands. So it started with a maximum flow rate of 200 meters cubed per hour, and the aim is to increase that capability by scaling up to different facilities. But that's what they have at the moment. So in terms of the development, in terms of operating ranges, they started with a small system based on a primary reference flow standard with flow rates of up to 25 meters cubed per hour and an uncertainty of 0.2%. Over time, towards the LNG3 project, the uncertainty has been reduced and the reference flow rates have been increased. So there's now a maximum flow rate of 200 meters cubed per hour and an uncertainty of 0.15% at the VSL facility. And the aim is to keep improving on this and develop new facilities which are ultimately traceable to the primary standard developed by VSL. Within this project, NEL are working on Work Package 1 in the LNG3 project. And this has a focus on the effect of upstream disturbances and meter insulation on the measurement results from the flow meters tested. There's also a focus on the Coriolis meter response time, thermal stability, and the effect of temperature on Young's modulus, and ultimately the flow meter error. We also investigated and demonstrated the feasibility of using a cryogenic piston improver as the primary reference for the flow measurement. And there was additional measurement techniques studied, including laser Doppler velocimetry for verification of the flow meters. And within the project, there was also a feasibility study for explaining how you would scale up to the next stage and increase the flow rates to 1,000 cubic meters per hour. So again, I can't talk about any of these in too much detail, but if you're interested in this project and the outcomes from it, then there are reports and journal papers published, which you can find from the project website, which is shown at the bottom of this slide. The last application we want to look at is carbon capture and storage, which really for NEL means measuring carbon dioxide and CCS mixtures accurately in terms of flow rate. And obviously this is needed as a supporting role for many of the technologies and gases that will be worked with to mitigate the effects of global warming and carbon dioxide emissions. So it's needed if you're using biofuels or fuels derived from fossil fuels, then you need to capture the CO2. Otherwise, you aren't reducing CO2 emissions. Now, in terms of the actual accuracy requirements, the EU emissions trading scheme requires an accuracy of 1.5% on the overall mass of CO2, whether it's derived from flow rate measurements or otherwise. This could be very challenging because carbon dioxide has fluid properties that can be very difficult to work with, depending on your operating conditions. The challenge is that the critical point and the trickle point occur at pressures and temperatures which are quite close to typical operating conditions. So the critical point especially is it occurs at 31 degrees C. So what this means is that small changes in temperature could result in quite large changes in fluid properties, and you're always quite close to the phase boundary for many applications. So it has implications for the phase of the fluids. There could be a phase change, or there could be changes to fluid properties, including density. So you could imagine on large-scale CCS schemes, if you have to transport carbon dioxide mixtures or CCS mixtures across a large distance, then it's going to be quite difficult to maintain fine control of the pressure and temperature to make sure that you don't move into two-phase regions or change the fluid properties without, to a range that exceeds the flow meter performance. So this is only becoming more complicated when you think of the effect of mixtures and impurities as well. So the phase diagram for carbon dioxide on its own is challenging, but when you have mixtures, then what happens is you have various phase diagrams depending on the mixture compositions. So we can see some examples here. We have carbon dioxide and hydrogen. We have carbon dioxide and nitrogen, CO2 and methane, and CO2 and carbon monoxide. And they all have different phase diagrams. So you can imagine small changes in each of these impurities could shift the fluid properties. And it means that your previous assumptions about the phase behavior might not be correct. So there is a real need to develop new equations of state and new fluid properties knowledge in this area. So as we see it, there's various challenges in terms of accurate CO2 measurement and CCS mixtures measurement. There needs to be accurate sampling, so you know exactly what is in the mixture. There needs to be a greater understanding of the phase behavior for these mixtures, so that includes development of new equations. And the flow measurement as well has to be accurately specified. So depending on the conditions, you could have CO2 in the gas phase or in the liquid phase. This is going to affect the meter selection that you make. And it's going to be especially challenging if you can encounter two-phase flow conditions, because most flow meters are not well suited for those conditions. So it's a very challenging area, and the exact technical solution to it depends largely on the operating conditions, which are not that well detailed at the moment. But regardless of this, we've done some work in this area already. We did some testing with CO2 in the gas phase, and it was actually mixtures of CO2 and nitrogen. So we tested in our wet gas flow facility, although there was no liquid present in these tests. And we tested in quite a large scale meters of 6 and 8 inch nominal bore. And we tested ultrasonic meters, Coriolis meters, and orifice plates. And we did that a number of years ago, actually, but we still have that capability now if it becomes of interest again. We also have a static CO2 facility, which is used for testing the performance of fluid property sensors and sampling systems. It's not a flow measurement facility, and we can circulate the CO2 and the mixtures, but the focus is not on testing flow meters exactly. And this facility can operate at pressures of up to 150 bar across a wide temperature range. So it can work across the full CO2 phase envelope, which is very impressive. Finally, the last thing that we're doing on CO2 at the moment is we're supporting a PhD program that is operated by Heriot-Watt University. So this isn't our work. This diagram on the screen, this is from a previous PhD, which was on the same subject. So this was the development of a small gravimetric system for testing, well, at the time it was a Coriolis flow meter, and it was testing it with various CCS mixtures. So the second stage of this work is something that we're going to sponsor, and it'll be carried out by a PhD student at Heriot-Watt University. And the focus will be on a greater range of fluid property ranges and with a greater range of flow meter technologies. So this should be very interesting. And that brings us on nicely to the last part of this presentation, which is the Clean Fuels Metrology Centre. So this is an initiative led by NEL on behalf of the National Measurement System. And this is really a scheme that we're getting together. We're starting up with various different partners, including Coventry University, Heriot-Watt University, as you've just seen, Glasgow University, South Lanarkshire College, and the Energy Technology Centre, who are one of the companies that are basically our neighbours on the site that NEL shares. And the overall aim of this Clean Fuels Metrology Centre is to provide metrological tools to allow reliable, safe, accountable operation of decarbonised fuel supply systems. So there's various different parts of the Clean Fuels Metrology Centre. Now, obviously, our focus is going to be on flow measurement standards. So part of it is traceability and providing UK's traceability for flow and density for various different fluids, including hydrogen, CO2, potentially ammonia and LNG and various other fluids. On the R&D side of things, part of the reason for this is that we want to have a greater collaboration with academia. So that's why we have so many universities involved in this, as well as a greater collaboration with industry as well. So we really hope to be able to take a wider approach to the research that we do and be a bit more outward facing, because the challenge of net zero emissions is something that's much larger than just NEL alone. There's also going to be a focus on KT, and that's always been an important thing for NEL. That's why we run these webinars and similar events. So to date, the current and upcoming activities that we're working on in terms of the hydrogen and CO2 measurements, these are all part of the plans for the Clean Fuels Metrology Centre. And in terms of the hardware itself, we're really talking about construction of new test facilities at NEL. So starting with the domestic gas flow meter facility, which you've seen already, but we will also develop portable gravimetric standards for hydrogen refueling stations. So you've seen some examples of those already, and NEL are also going to develop theirs. But those are the priority areas at the moment, and we'll basically move out from there to larger applications with different fluids. So the point we want to get across at this point is that we are very open to collaboration. We want to have closer links with academia, but also with industry, because there are challenges that affect us all, and there's different roles that we can play in solving those challenges. But that takes us to the end of the presentation. There's some upcoming events that you might be interested in. So there's the focus group, which usually is hosted at Aberdeen and Norwich, alternating, but obviously it's going to be an online event. We also have the Produced Water workshop, which is still planned for Aberdeen, so that might be a live in-person event. The North Sea Flow Measurement workshop as well in October, and there's various lunches and learns, and there will be more webinars as well. But at this point, I'd like to thank you for your attention, and I hope you found this webinar informative and interesting. We have a few minutes left if you want to ask questions, so I'm going to have a look at the chat and see if anyone has submitted questions at this point. But I just want to thank you for your time, and thank you for your attendance.
Okay, thanks very much for that, Mark. As you say, it's a lot of really interesting work going on there, really informative. I think we've got time maybe for a couple of questions, so I don't know if you want to kind of pick a couple, and then hopefully we should be finished within the hour.
Yeah, that's fine. I'm just looking at the question and answer window right now. Have to make it bigger. Yeah, we have a few questions already. So we have a question: how much work has been done looking at equations of state for hydrogen or hydrocarbon mixtures for domestic supply, and are they accurate? The answer for that is not a lot of work has been done with hydrogen mixtures. So the equations of state, which are commonly used for pure hydrogen and for mixtures of other gases, if you try and apply these for hydrogen, in most software packages, you'll get a warning that basically says you can't really trust the results. And I'm not an expert in fluid properties, but I've been told this is based on the nature of the reduced parameters for hydrogen. They're in quite a difficult range. But the overall point is that more work has to be done in this area. So potentially that was a concern for our domestic gas metering rig, because we have mixtures. You know, we're measuring the pure fluids before they're mixed, but ultimately at the test section, we need to know the density of the mixed stream. Now, luckily for us, the pressure at our test section is only coast atmospheric, so you tend not to see significant compressibility effects. So you can approximate it almost as an ideal gas mixture. And we've looked into the background of that, and we've looked at experimental data which verifies that claim. But for higher pressure applications, this is a problem that needs to be solved. So there have been research programs proposed in the past, but they haven't, to my knowledge, they haven't taken place, and that work still needs to be done. The next question is, are there any flow meters showing promise for CO2 applications? Can you share the NEL test data in CO2? So the test data that we have from the wet gas facility, that was customer work. So I don't know how much we can actually share about that. I would need to check what permissions we have to share the findings. In terms of other flow meters, as I said, the Heriot-Watt University, they built the gravimetric system to test a Coriolis flow meter, and they found that with hydrogen mixtures in the gaseous phase, the accuracies they were calculating were within the desired range. So I think they were getting errors of less than 1% for that flow meter. So that is obviously promising. There has been other applications. There's been other tests with CO2 liquids, but off the top of my head, I can't name those references. I can look them up after this webinar though. And a question about the refueling station primary standards. So what accuracy do they achieve? Yeah, so the portable gravimetric standards, the field test standards that I mentioned before, the claimed measurement uncertainty for those is about 0.3%, and there is publicly available uncertainty budgets for those. So the papers that I mentioned previously, you can scrutinize those yourself and see if you think those claims are reasonable. But also the field testing that took place, it suggests that the claimed measurement uncertainties for those systems are accurate, because we saw some results where the flow meter performance was, well, the errors were very low. So it suggests that the uncertainty is within that range of about 0.3%. There is more evidence needed to verify this though. So there are intercomparisons planned between those gravimetric standards as part of the Metrology for Hydrogen Vehicles project. So that project is due to finish in August, but there's still intercomparisons to take place. And there will also be additional intercomparisons in the follow-on project, MetroHive 2. But so far, the claimed measurement uncertainty of 0.3% for those systems does seem to be accurate.